Hello everybody and welcome to this webinar, Developing Robotics Applications with MATLAB, Simulink, and Robotic System Toolbox. My name is Carlos and I am an application engineer working in MathWorks office in Natick, Massachusetts. To start with a short intro about myself, I've been working with robotic systems for more than 10 years already. I did my PhD in robotics in Japan, studying full-size humanoid robots, and after this I worked with autonomous robots doing localization, path planning, SLAM, and other types of interesting robotics algorithms. So yes, today we're going to talk about robotics applications, but I would like to start by formulating a question. What's that question? Well, what are you doing with robotics? And I believe this is a very important question because, as you all know, robotics is a very broad area, and it seems everyone is doing robotics nowadays based on what we see on the news. So let me simplify the world into three types of activities in robotics. Maybe you are building robots. That means that you want to build a robot with great robustness and durability. So if this is your case, probably you want to design a controller to drive the robot, but before this you need to have a plant or a simulation of your robot. So you start with your plant, then as I said, you design a controller or an algorithm that actually commands and drives the robot, and after this you want to deploy to hardware so you can target an actual microcontroller or microprocessor that runs on the robot. So MathWorks offers a comprehensive list of tools for modeling different types of robotics components. So you can see we have already customers that have adopted our tools for building their robots. We have the Festo Bionic arm here on the left side, and we have the DLR from the German Aerospace Institute humanoid robot. So these two systems are advanced robotic systems. As you can see, they perform advanced maneuvers, and the interesting part is that they are built using our tools. So if you want to know more about this workflow, I invite you to check the webinar, How a Differential Equation Becomes a Robot. This webinar contains the details of this workflow. Coming back to our classification, we have a second group, and that's the education space. So this is interesting because many professors contact me and they tell me that they want their students to program a robot anywhere, anytime. This is an interesting challenge. So I see two options, right? The first one is to provide any student with a low-cost hardware robot that could be a robot running based on a Raspberry Pi or an Arduino board that are popular low-cost hardware boards for robotics. So if this is the case, I'm happy to share with you that MathWorks offers a long list of hardware support packages so that students can program robots built with low-cost hardware inside MATLAB and Simulink. If you want to know more about this, please check this link that I'm showing you here on the slide. But there's another option. Let's say you already bought a commercial off-the-shelf robot, so this could be a more expensive piece of hardware, so it's very difficult to provide every student with this type of robots. But then you can leverage simulators. Let's say there are standard simulators nowadays that you can design your algorithm. So professors want their students to design their algorithm using the simulator, and they want to have MATLAB and Simulink connected to the simulator. So if this is your case, I'm happy to share that Robotic System Toolbox provides this functionality, but we're going to talk about this later on the webinar today. And the third group is also related to the previous one. You want to develop robotics applications using existing robots or simulators. So maybe you bought a robot, you already built your robot, and if this robot, let's say, already has all the hardware components, you want to start developing advanced robotics applications. This is the core of my presentation today and how you can use MATLAB, Simulink, and Robotic System Toolbox for this. Let me show you some examples of the type of applications that I mean with this. So here you see on the left side of my slide a Turtlebot navigating autonomously through a floor plan using a representation of a map here in MATLAB. And on the right side you see Baxter robot. It's playing checkers against a human. So these two robots are commercial robots, and they share something, is that they both provide a ROS interface, that is the robot operating system. So now with Robotic System Toolbox you can connect to these two robots and develop your algorithm in MATLAB or in Simulink. So for example, these two examples that I'm showing you here, the interesting part is that all the algorithmic part is running in a computer running MATLAB. So for example, on the case of the Baxter playing checkers, we are using functionalities provided by Computer Vision System Toolbox, Image Processing Toolbox to identify the board, detect the pieces. Then we are using MATLAB functions to actually move the robot and do some path planning. And finally, send an end effector command so the robot can play checkers against a human. So these are like just examples of the type of applications that you can develop. But of course, it depends on your area. Some of you guys may be doing controls. Maybe others can be doing computer vision. Others may be just interested in doing data analysis. All of this is possible now with MATLAB, Simulink, and Robotic System Toolbox. So in terms of the agenda of the webinar today, I would like to start by showing you some features of MATLAB ROS interface. How can MATLAB connect to the robot operating system? Then I will talk about some of the built-in robotics algorithms that Robotic System Toolbox provides. And finally, I'm going to talk about the Simulink ROS interface, because Simulink ROS interface allows you to connect Simulink, and also you can generate a standalone ROS node that can run on your robot. So to start with the MATLAB ROS interface, let's ensure we have all the concepts clear. So the interface to ROS-enabled robots and simulators is an important part of our toolbox functionality, as I mentioned. In case you are not familiar with the robot operating system, or most commonly known as ROS, I just want to give you a short intro. I know some of you may have already used ROS, but I also know some of you that probably this is the first time you hear this concept. So this is just a very short introduction. At its core, ROS provides infrastructure for distributed communication in robotic systems. It's also called sometimes a middleware because it runs on top of Linux. The important thing is that ROS contains a collection of packages or libraries for solving common robotics problems. So this includes drivers to interface with sensors and actuators that are very commonly used in robotics, and it also provides some libraries for robotics algorithms. So you may be asking, what does it mean when we say that MATLAB and Simulink are connected to ROS? Well, it means that now you can implement your robotics algorithms in MATLAB and in Simulink, and then use ROS to test these algorithms in a physical robot, or it could be also a simulator. So to assist you in the development of this type of algorithm, Robotic System Toolbox also provides built-in algorithms related, for example, to path planning and path tracking, which are very, let's say, popular algorithms in robotics. So how do we pass data in ROS? And that's another concept that I want all of you to have very clear understanding. There are two ways. So usually communication and processing in ROS happens through nodes. So you can exchange data through what we call ROS messages. And there are two ways of sending and communicating data. So ROS nodes can publish topics, and the nodes that are interested on getting that data subscribe to those topics. So that's why we call it publisher-subscriber scheme. There's another way that it's a classical remote procedure call, and it's a client-server way of communication. So that means that when the client needs information from a particular node, he requests that information, and then the service, when the information is ready and the data is ready, replies with a response, and then the client is happy because it gets its data. So MATLAB would be one of these ROS nodes in your robotic system, as you can see here on the figure. And probably this robotic system, it's complex or it's distributed, so it can have many components. So you can have another CPU here with different types of algorithms. You can also have ROS nodes that interface with the sensors or the actuators. In general, a robot can be comprised of many different nodes, right? And now you have MATLAB and Simulink connected to the ROS network. So I know that right now you're interested on seeing the demos of the MATLAB ROS interface in action, so it's a good time to switch to MATLAB. The first thing that we want to verify is that you have Robotic System Toolbox installed. In order to do this, we type VER in the command window, and we search for Robotic System Toolbox. So as you can see here on my machine, you see that I have Robotic System Toolbox. After this, I'm going to use a script to show you the main features of the product. The first function that I want to talk about is the ROS init function. This is a very important function because it allows you to create a ROS master in MATLAB or to connect to an external ROS master. If I want to connect to an external ROS master, you just need to specify the IP of that, could be robot or simulator. So in this case, I'm just making up some IP, and that will connect to that external ROS master. If you just call the function, as I'm going to call it here, with no parameter, then MATLAB is going to initialize a ROS master, as you can see, and is going to initialize the global node in MATLAB. Now I'm going to create an instance of a robotic simulator that we created in MATLAB that provides a ROS interface. So it's also using Robotic System Toolbox functionality. So I'm going to accommodate my screen so you can see both MATLAB and the robotic simulator. So you can see what does this mean. So it's a mobile robot simulator, as you can see on the figure, has some laser range scanner simulation, a bumper sensor simulation, odometry sensor as well, and it's a differential drive robot. So if now we execute ROS node list, you see that the only node on the ROS right now is the MATLAB global node. How about ROS topic list? So we execute this piece of code and we see these 5 topics corresponding to the velocity, that is the topic that we publish in order to move the robot, the bumper sensor simulation, the odometry topic, ROS out, which is standard, and the laser range scanner topic. If you want to obtain more information about a particular topic, we use ROS topic info, and that will tell us the type of message that the topic uses for transmitting data, as well as the nodes that are publishing to that topic. In this case, it's just MATLAB global node and no subscribers. We also have the echo functionality if you want to get data immediately about a particular topic. So let's see, for example, here in the case of the odometry topic, and we see the position and the orientation of the robot. So on this case, the robot is in 10.33, 10.33, and visually we can effectively verify that the robot is in that location. Let's continue exploring some of the functions. You also have the ROS message show functionality if you want to get more information about a particular message. So in this case, let's get more information about the sensor message laser scan, and that tells you the different parameters that that message has. If you want to get data now from the robot or simulator, we have to create a subscriber. So in this case, let's create a subscriber for the scan topic, and we name it scanner. If we verify here on the MATLAB workspace, we effectively see here that it created a subscriber object. And if we want to get the data, or the message from that subscriber, then we have different ways. You can use the receive function, that is a blocking function, as I'm showing you here on the slide. Or we can also use that latest message field of that scanner object, or you can specify a callback that will trigger every time that you get a new message. So in this case, let's just use the receive function. This 5 is just a timeout that you can specify. So now we got the data of that message. So if I type here in the command window laser data, we see the different parameters of that message, right? The different information. Let's say that now we want to visualize that data. So for, let's say, advanced data types, we have some overloaded functions. So for example, here, look that we are using the plot function directly on the scanner.latest message object. So if we execute this function, we actually see the plot of what the laser range scanner is returning. So on the right side, we effectively see that the robot is on one corner, and that's what the XY plot of that message is showing us. So that's for getting data from the robot. What about if you want to send data to the robot? So in that case, we need to create a publisher. So we use the ROS publisher function in order to do this, and we specify the topic that we want to publish. So if I execute this piece of code, this returns 2 objects: the publisher itself and the message that you're going to use to publish to that topic. So now we configure the message. In this case is velocity, so I specify the linear velocity, the angular velocity, and then we use the send function using the publisher and using the message to actually send data. So if you see and you pay attention to the simulator, and I'm executing this piece of code multiple times, you see that the actual robot is getting the information and moving accordingly to the information on the message. Let's reset that message, send a 0 command to the robot. And now let me show you how easy it is to create an algorithm, a simple algorithm. So in this case, I just have a while loop. I'm getting the sensor data from the laser range scanner, and I'm just going to detect if I'm close to a wall or not. If I'm not close to a wall, I drive forward. I send a linear velocity command, as you can see from the simulator. If I detect the wall, the robot should stop in order to avoid a collision. So let's see if it effectively is what happens. So it goes straight, and it should detect that wall at some point. And now it detects the wall and it stops. So that's to show you just an example of how easy it is to start prototyping and creating your own algorithm. So you might be asking, okay, do we support also services from MATLAB? Yes. So if you want to see the services, then you use ROS service list, and that shows you the services that this simulator has. In this case, reset world, new robot pose, and reset poses. And if you want to call that service, you use the ROS service or SVC client function. You specify the service name, and then we call that service. And if you notice, the simulator went back to the initial pose before I started moving the robot, because that's what actually this service functionality provides. And finally, we want to close and let's say shut down the network. We use the ROS shutdown function for that, and that disconnects from that ROS master that we created in MATLAB. So that's one important functionality. Now I want to show you another functionality related to importing ROS bags into MATLAB. Let's open another script that I use to showcase the basic functionality of the ROS bag import. So I already have a ROS bag that I recorded. I believe some of you already have ROS bags that you have recorded from the hardware or from simulators. So in my case, my ROS bag is robot_circle.bag. And with the ROS bag function, I load the file. One important thing is that we are not actually reading all the data from the ROS bag, because as you know, ROS bags tend to occupy a lot of space in memory. So we are just loading the file. Later, I'm going to show you how you can especially read the message from the ROS bag. So now we see that this is a bag selection object with these properties, right? You see the starting time, the end time, number of message, the available topics, and the message list. Let's explore the available topics. So here we can see that we actually recorded 3 topics: the camera depth point, the odometry topic, and the scanner topic. Let's select a particular topic. So in order to do that, we use the select function. And if we want to read the messages, well, when we use that read message functions applied on that ODOM object that we created on the previous step. So let's execute this piece of code. And then I'm saying, okay, as a cell array, show me the first instance, the show details, so we can see the information of that message of the odometry topic. We can also read it as a time series. So for example, here we can read the XY position of a time series. So we read this piece of code, is converting that information to a TS object that is a time series, and logically we can visualize the data of the odometry topic quickly. Let's see a more advanced or more interesting topic. So here is the camera depth point. So as well, we use the select function to get all the depth camera points. Then we're going to get just one of those messages with the read message function. And then we use our scatter3 function to visualize a point cloud. And if we execute this function, now we can see what the actual robot was looking. So we see it was like a table on a corner. That's the image. So this is a very powerful feature that you can quickly visualize the point cloud. Let's select a bigger piece of data. So as well, we use the select. As you already know, we use the read messages function to get all that point cloud. And then we can use and leverage computer vision system functionality to visualize the point cloud as an animation. So as we can see here on the slide, we actually see what the robot was looking, and we actually see the full scene there. Finally, we can close and clear all our data. So those are the features related to ROS bag functionality. Coming back to my presentation, we showed how to create ROS nodes, publishers and subscribers using MATLAB ROS interface from Robotic System Toolbox, how you can call and provide services. You can also access the ROS parameter server. I didn't show this on my scripts, but it's also a capability. You can also have access to the ROS transformation tree. And as we saw, we have the powerful feature of reading, filtering, and extracting messages from ROS bag files. So let's go back to our agenda. Our second item today is about robotics algorithms. Robotic System Toolbox provides built-in robotics algorithms that can help you to develop this type of robotic application. As you can see, is the Turtlebot going from one point to another and using a map in order to achieve this. An important thing to mention is that these robotics algorithms do not depend on ROS. Of course that you can test them using a robotic simulator or a robot that runs ROS, but the algorithms itself do not depend on ROS. So let me switch to MATLAB so I can start showing you how you can develop this type of application. I'm going to open a script here in MATLAB that contains the main features of the algorithms that come with Robotic System Toolbox. I'm going to accommodate my window so we can visualize my MATLAB and the image or the figures that we create on each step of the script. So here on this line of code, I'm just reading an image file, and that image file contains the image of this floor plan. And then we created a binary occupancy grid object. That is one of the objects that comes with Robotic System Toolbox. You specify the resolution, and what that does is basically, as you can see here, this is the image, but it contains dimensions as well. So now we have a map representation where that binary occupancy grid, you can see it as a matrix where a 1 represents that the space is occupied and a 0 represents that it's empty. So it's very convenient because you can use this representation to do path planning. And after creating this map or binary occupancy grid, you can visualize it by using the show command, as I'm showing you here on my script. Now we're going to inflate that map. So as you can see on the figure, basically we make the walls and the obstacles thicker, just with the objective that we want to consider the robot as a point object. And instead of considering like the geometry and width of the robot, we just make it a point and we make the walls and the obstacles thicker. Again, this is also a standard method in robotics. Now we want to do path planning. So we can create a probabilistic roadmap planner. That's a standard planner in robotics. And in order to do this, we create the object from Robotics System Toolbox called a PRM. It receives as an input that map that we inflated, and we specify some parameters, the number of nodes. So as you can see here on my figure that is going to be created soon, you will see how we place nodes randomly on the environment. And what's the idea behind this? You can see that the image also shows that those nodes are connected with lines. But if you pay attention to the figure, you will notice that the lines are collision free. Because remember that our objective is to do path planning. That means that we want the robot to go from one point of this map to another point, of course, without colliding. And this PRM object, you can also visualize it, as you can see here on the figure. The next step is we want to specify a starting location where the robot is initially, let's say the 0, position, the end location, and then we use the find path command from that PRM object, specifying the start, the goal. So if we execute this piece of code, now you see here on the right side the actual path. So this is the 0, position, and this is the goal location. Now we found the path. These are represented by these X, Y positions of these nodes. And this is what the robot should follow in order to go from the goal to the end location. So that's one part of the problem. Now you may say, Carlos, but we actually need some kind of controller so it drives the robot along that path. You are correct. So that's why you can use from Robotic System Toolbox the Pure Pursuit object. This is also a traditional method in robotics in order to drive a robot through a path. So the input is the path of this controller. So as waypoints, you specify the path that the PRM found. And then you can configure some parameters like the desired linear velocity, the maximal angular velocity, and the look ahead distance that are parameters of this controller. So let's execute this piece of code. We created that Pure Pursuit object Finally, we are going to create, let's say, a robotic simulation that we have here in MATLAB in order to visualize the robot following the path. So now you can see here on the right side that we actually have a representation of that robot. And then we are going to execute that controller in a while loop. Why? Because it is a controller, it has a step method associated with it. So as you can see, it receives the current pose of the robot, it receives the controller, of course, and it outputs the linear velocity and the angular velocity for that step. And then we just drive our robot with those commands. Let's see what happens. So now I execute play, and you see that the robot follows the green path based on those parameters of that controller, and it drives the robot from the start location to the final location. So to summarize, I show you how you can import a map using the binary occupancy grid object, how you can as well inflate this map, then create a probabilistic roadmap object that samples the environment, create these nodes, connects the nodes. Then you can actually find the path from one starting location to a final location, and then we use the pure pursuit path tracker to drive the robot along that path. So as you see here, we prototype our algorithm just using MATLAB, right? We have everything here in MATLAB. But at some point, we might be interested to connect to a robotic simulator. So actually, I have a robotic simulator, and I'm going to show you how you can, with the same code, test it with a real robotic simulator. So I open here, I have Gazebo, and it has the Turtlebot, as you can see here. And maybe you already realized that the floor plan that I showed you before corresponds to the floor plan of this environment. So I'm going to open another script that actually shows you how we can connect to Gazebo, but let me show you this interesting thing first. So I'm going to show you both of the script, the one that I showed you before, and this script that we're going to use to connect to Gazebo on the same screen. Why? Because the first 6 steps of these two scripts are exactly the same. As you can see here, first we read the PNG file, we inflate the map as I showed you before, we create a PRM, then we create a pure pursuit controller, we find the path. So the only difference with this script is that here on this script, we are actually also connecting to Gazebo. So that's why I specify the IP address of my virtual machine. I'm going to show you later how you can do this. And then is the same while loop that I showed you before that drives the robot. And of course here, because we're using Gazebo, then we use Robotic System Toolbox MATLAB ROS interface to send that velocity, linear velocity, and angular velocity to the robot. But other than that, is the same script as I'm going to show you now. So let's execute this script, but I want to show you at the same time my robotic simulator that I have here and my actual script. As I said before, if you want to verify the IP address of the robotic simulator, this is a virtual machine, so you can just access here the command window and execute ifconfig. So let's execute this file and see what happens. So I'm going to run the whole file all at once. So as you're going to see, it has to show me the same, let's say, visualization that you saw before in order to do all the path planning. So now we're reading the image, it's doing the path planning, it's creating all that object. And now here you can see my actual MATLAB simulation, but you can also see on the right side the Turtlebot navigating through the environment and going from the 0, 0 location and going out of the door. That is what it's supposed to do. Remember that all the algorithm was prototyped, created, developed in MATLAB, and we are also using the built-in robotics algorithms related to mobile navigation that I showed you before. So as you can see, this kind of co-simulation workflow is very powerful, and there are many applications that you can start developing using this functionality. So now I would like to go back to my presentation. So I show you the different robotics algorithms provided by Robotic System Toolbox and how you can use them to design cool robotics applications. Now I would like to continue with the final item of our agenda, and that's the Simulink ROS interface. I'm sure this is going to be very interesting for you guys because many of you design robot controllers or robot algorithms in Simulink. For this interface, I would like to emphasize a 3-step workflow. The first one is, of course, to design your algorithm in Simulink. The second one is that you can test your algorithm either in Simulink with a MATLAB Base simulator, that's the one I have been showing you throughout this webinar, or you can also connect to an external simulator such as Gazebo that I've also shown you this workflow today. After you test your algorithm, then if you have our coder tools, you can actually generate a standalone ROS node from Simulink. That means that you can generate the C++ files that will actually run on the standalone mode on the simulator or on the robot hardware. So this is a very powerful workflow. I know you are very interested in seeing this, so let's switch now to Simulink. I'm going to open a Simulink model that I have created that has the blocks from Robotic System Toolbox. So first of all, if you open the Simulink library browser, you go to Robotic System Toolbox, you will see that you have three blocks: the blank message, the publish, and the subscribe. So how do we use those blocks? Well, let's use this model to explain how you can use them. So what I really like about Simulink is that you can clearly visualize the different components of your model. So for example, here we have the communication layer in charge of getting data from the robot. We have the algorithm that takes that data and computes an output. And here we have the communication layer in charge of sending data back to the robot. So to get data from the robot, we use the subscribe blocks, and we subscribe to the different topics. In this case, the bumper, the odometry, and the scan topic. To send data to the robot, then we have to publish, right? So we're using a publish block. We create a blank message of type twist. We configure the message, and then we publish that data to the commands velocity topic. And our algorithm is here in the middle. In this case, I'm using a Stateflow chart. For those of you that haven't used Stateflow, well, Stateflow is our library in Simulink that is specialized for modeling instantaneous events, finite state machines. And I know because most of us here are roboticists, you know that finite state machines are very commonly used in robotics. So in this case, this algorithm just drives the robot to an XY position. So it has a, let's say, a routine that is in charge of correcting the orientation based on the odometry data and the desired orientation. It computes a desired angle and, let's say, a linear velocity and an angular velocity. And it has also an obstacle avoidance routine that if we collide with a wall, it corrects the orientation. So we want to test this algorithm, right? So what's the idea here? First, we can use a MATLAB Base simulator in order to do this. So I'm going to use the one that I've been showing you before. So let's go back to MATLAB, and I'm going to use, first I'm going to initialize a ROS master and a global node in MATLAB, and I'm going to create an instance of that robot simulator. So here's the robot simulator, and I'm going to bring my Simulink model to show both at the same time. You of course need to configure that network address. So Simulink, if you want to do this here, you go to Tools, Robot Operating System, Configure Network Addresses, and you ensure that it's the default. So if it's the default, Simulink will use the ROS master URI or the local host, as in this case. Now we hit play. And as you see, the robot is trying to reach, on this case, the 0, 0 location that is here on this corner. But well, that's a very tough one. So let's try to make it easier for him. So I'm going to stop my simulation. Let's go to randomize location to make it a more interesting starting location. I think that one is good. And let's try to reach the 8, 8 location. So we can go here and we say 8, 8 is my desired location, and we hit play. So now the robot should try to reach the 8, 8 location, and of course it's correcting the heading, and it's trying to reach that position. Probably that one was too easy. Let's try to make a harder one, and at the same time I'm going to show you the Stateflow chart. Let's hopefully it collides with the wall. So then here you say that it collides, it switched to the other state. You see how Stateflow shows me the different state on which the state machine is. And now it's switching between these two states until it reaches the 8, 8 location. So then it reached and it stopped, so goal reached. So that's one part of the algorithm, right? We designed the algorithm, we tested our algorithm, in this case using the MATLAB Base simulator, but we can also use an external simulator. So I'm going to close here my MATLAB Base simulator. and I'm going to bring back my virtual machine with Gazebo. And I still have my Turtlebot here, but I have a different environment. This is an open environment. To test it with the external simulator, I can use exactly the same model with the only difference that I need to connect to a external ROS master. So I go here, I say custom, I specify the IP of my virtual machine. In this case, that's the IP. I hit OK. I hit play, and I should expect my Turtlebot moving and trying to reach the 8-8 position, and effectively that's what it's doing. So as you noticed, I just changed the IP and I could test with the external simulator. That could be the hardware, of course, if you want to test directly with the hardware. But remember that one of the, let's say, advantages of simulation is that you can test all sort of crazy stuff, design your algorithms without like having to test in the actual hardware. That could be expensive. So for example, here I can change again the desired orientation. Let's say I want to go to 0, 0 again. And then the robot goes to 0, 0. So now I'm just changing the goal position, but imagine that this is a controller. You can change the value of the gains and see on the simulator how changing that value is actually changing like the behavior of your controller. So here the robot is trying to reach against the 0, 0 position, and it arrives to the initial position. So we can stop here our simulation. And now it's a good time to switch to our final step of our workflow, the one that I emphasized at the beginning. And if you remember, that was if you have the coder tools, you can actually generate a standalone ROS node. So how does that work? If we go here to simulation, model configuration parameters, I want to show you the options that you will have right now. As target hardware, we have the robot operating system. We have the tool change that will be Catkin. And if you hit here the build button, that will generate two files that I have already done it here in sakes of time in your current directory. So here, if I go back to MATLAB, you will have these two files. First, it will be a Linux shell script. And the second one is this compressed file that will have your model like name and the TGC extension. But if you just explore the contents of that file, you will see that it will contain the CPP and the .h files that were generated that correspond to your Simulink model. So what's the idea? The idea is that now you deploy these files to the hardware, to the like ROS system, or to the simulator itself. So because I'm showing here my demo with a virtual machine, the idea is that you need to deploy this to the virtual machine. You can do this using a standard, let's say, Linux PCP commands, or if it's a virtual machine, most of them, they support drag and drop. So I have already done this. So I'm going to show you here my virtual machine. Here I have the two files, right? The sh Linux shell script and the compressed file that contains all the CPP and .h file. And the idea here is that you need to execute that shell script, right? You point to the TGC file and you create a Catkin workspace. So in this case, my Catkin workspace is like, I name it Catkin _ws _Simulink. You hit play. So what it's happening right now is that Simulink is taking all those files, compiling them, and building a standalone ROS node. So now you see all the process, it's almost done, it's 100%, and it finished compiling and building that ROS node. So the first thing you can check here, this is all their C++ and .h files in the source directory of your Catkin workspace. And then if you go here to the lib directory, you will see the actual object or the generated standalone ROS node. And why is this powerful? Well, because now you can actually execute this ROS node. So as you recall, I stopped my Simulink model. So I'm going to execute my ROS node and I'm going to show you the simulator. You see now that the ROS node is being executed on the standalone mode. So that means it's running on the Linux system, on the ROS system, and it's reaching the 8.8 location, right? So as you can imagine, this is like the final step of our workflow. It's very powerful. Just to recall, let me switch back to my slide that had the 3 steps. First, I show you how you design your algorithm in Simulink, and in Simulink it's very nice to see how everything is separated as a communication layer, and your algorithm itself, you get data, you do something with the data, and then you send that data back to the robot. We tested the algorithm using a MATLAB-based simulator, or with Gazebo as well, having Simulink connected to the simulator. And finally, when we were satisfied with our performance, we generated a standalone ROS node from Simulink that could generate on the system itself, or if you have the hardware, you can actually just run it from the hardware. So this is a very powerful workflow, and that's one of the key features of the Simulink ROS interface. So fellow roboticists, we just covered the 3 items of our agenda for today. So to do a recap of all the interesting things I show you, we talk about the MATLAB ROS interface and how now you can create ROS nodes, publishers, subscribers, and services from MATLAB, and how you can design and test your algorithms in MATLAB, as well how you can connect to external robot simulators such as Gazebo and VREP. And if you are satisfied with your performance on simulation, you can test your algorithm with a physical robot just by changing the IP address that you're connecting to. And if you have data you have recorded from the robot or the simulator, you can also import ROS-backed log files into MATLAB. We also talk about the Simulink ROS interface. I show you how you can publish and subscribe from Simulink models and how easy it is to visualize the communication layer and the algorithmic layer from your model. And if you have our coder tools, you can also generate a standalone ROS node that will run on the simulator or on the robot. And we also talk about the algorithms in Robotic System Toolbox. So how you can now represent maps as binary occupancy grids, how you can use a probabilistic roadmap planner to do path planning, and how you can use our pure pursuit controller to drive a differential robot and do path tracking. I also mentioned that Robotic System Toolbox comes with coordinate system transformations, so now you can convert from quaternion to homogeneous matrices or Euler angles or angle axis representations. I would like to finish my talk today showing you other applications that we have developed using the features of Robotic System Toolbox that I just showed you. So here you see a user interface. On the right side, you see the Gazebo simulator running with a Turtlebot. And on the left side, you see a user interface that I've created in MATLAB, and it's doing extended Kalman filter SLAM. But what's the bottom line here? Here you see how we get data from the robot using the MATLAB ROS interface. So we're getting image data. We can see what the robot camera sees. We also are plotting the laser range scanner information, right? And we command the robot using the keyboard. So you will see how the robot starts moving. So we're using this laser range scanner information to detect corners on that floor. So in order to detect corners, we are using capabilities from Image Processing Toolbox and Computer Vision System Toolbox. And we map those corners. Here we use those corners as landmarks in order to create a map of our environment. So if I, let's say, fast forward this video, you will see how the robot continues navigating around here. And it detects the corner from the floor plan, uses those corners to localize itself, update the filter, and create a map of the environment. But what I want to show with this demonstration is how you can get sensor data, have like a very elegant visualization, right, of your sensor data, how you can also send data back to the robot, command the robot, and how you can design advanced robotics algorithms using all this functionality. So that's one application that I wanted to talk. Another cool application is visual odometry. So here we are leveraging capabilities of Computer Vision System Toolbox, especially the point cloud processing. So we have here a Turtlebot that is navigating through a kitchen. We are using, of course, Robotic System Toolbox to connect to this Turtlebot and get the point cloud data. And here we can see how we're doing point cloud stitching to create a 3D representation of that environment, and also how the robot is using this information to localize itself. That means that's why it's called visual odometry. So this is also a very advanced robotics applications that now you can develop like using the different capabilities from MATLAB, Simulink, and Robotics System Toolbox. And in this here, for example, if you're doing computer vision, you can also use Computer Vision System Toolbox. Now it's your turn. I've shown you different applications. I know that you maybe are doing controls, probably you're doing computer vision, image processing. It's your turn to design very advanced or cool robotics applications. I hope you enjoyed all the features I showed you today, and thank you for your attention.